We are very pleased to have Michael Kearns giving our keynote lecture. I'll tell you a little bit about Michael in case you're not familiar with him. Michael is a professor in the Computer Information Science Department at the University of Pennsylvania, where he holds the National Center Chair and has joint appointments in the Wharton School. He is founder of Penn's Network and Social Systems Engineering program, and he directs Penn's Warren Center for Network and Data Sciences. His research interests include machine learning, algorithmic game theory, social networks, and computational finance. He has a broad background in theoretical computer science as a whole. You might know him as the co-author of a popular text in Introduction to Computational Learning Theory. He has served as program chair of NeurIPS, formerly NIPS, AAAI, Conference on Learning Theory, COLT, and ACM Electronic Commerce. He's an elected fellow of the American Academy of Arts and Sciences, the ACM, AAAI, and the Society for the Advancement of Economic Theory. Outside of academia, Michael has worked and consulted extensively in the technology and finance industries. He's involved in the Venture Capital Fund Founder Collective and is a scientific advisor to the Financial Industry Regulatory Authority, FINRA. Beginning June of this year, he has a role as an Amazon scholar, focusing on algorithmic fairness, privacy, and machine learning within Amazon Web Services. So it's to share his thoughts on those last topics, on fairness and privacy and machine learning, that we've invited him to give the keynote at Pets Today. In November of last year, 2019, he published a book, The Ethical Algorithm, with co-author Aaron Roth, which describes, for a general audience, an emerging science of socially aware computing. The pets community, people listening now, has, in my opinion, been a leader in considering social impacts of our technologies. And in addition to the privacy issues that are a thing that this community thinks a lot about, ethical issues of fairness, transparency, and accountability are a growing concern among computer scientists as a whole. Michael seems to have a really positive message on these issues, and from what I understand, is going to argue that technologists have some power to solve them by embedding ethical goals into the design of their algorithms and systems. So again, the keynote will be 60 minutes. We'll have 30 minutes afterwards for questions and answers. And I think this is a really great opportunity to talk as a pets community about these ethical issues, things that I think underlie a lot of the academic work that we do, even if we don't really often talk about them explicitly in our papers. So please keep in mind your questions and comments to bring up after the talk. Please go ahead, Michael.
Okay, thanks very much. And thanks everybody for tuning in from wherever you are. So my name is Michael Kearns, and with my good friend and colleague, Aaron Roth, we have written a book that came out late last year called The Ethical Algorithm, which is really meant to be a general audience kind of popular science book, if you like. And as Aaron mentioned, I'm, first and foremost a career researcher in machine learning, really from kind of the algorithmic foundational side of things. And so what I want to do today is kind of overview the themes in the book. And, of course, Aaron and I have given variants of this talk many times to many types of audiences. This is an unusual audience for me in the sense that with respect to the topics in this book, there's, I think, a fair amount of expertise, especially on the privacy topic. So I've modified my slides and narrative a little bit to fine tune things. But let me start by kind of telling you what inspired us to write this book, which was really kind of a twofold force. First of all, as I think probably everybody listening is aware, there has been rising alarm from many camps in recent years over what we might consider to be antisocial behavior by algorithms, and very often specifically the algorithms involved with AI and machine learning. And there have been a number of very nice general audience books written expressing such alarms. So I've shown 3 of them here. And Aaron and I have read all these books and many others, and we like them very much. We think they do a very good job in very simple terms of viscerally describing the real harms that can come to real people from algorithmic decision-making, AI, and machine learning. Where we were disappointed in these books is when you kind of get to what you might call the solution section. So in each of these books, after describing, the horrors of AI and machine learning, you usually get to some late chapter or postscript that says like, well, what should we do about all of this? And, perhaps I unfairly characterize the answers as generally being of the form, well, we need better laws, we need better regulations, we need more watchdog groups, we really have to keep an eye on all this stuff. And just to be clear at the outset, my co-author and I agree with all of that. But the other force that encouraged us to write this book is that for many years now, both of us have been working on, designing better algorithms. And so our attitude was sort of like, well, yes, we do need better laws and regulations, but as scientists, we can also think about, making the technology better in the first place, rather than waiting for harms to happen in the world and then regulating or litigating them after the fact. And so we were very aware of the large body of science that's going on in the machine learning community and in communities like PETS to actually take these issues seriously and think about, dealing with them at the algorithmic scientific level rather than in the courts or our regulatory systems. And so we wanted to write a book that isn't really a direct response to books like the ones in front of you now, but that described to a rather broad audience about those scientific efforts, most of which we view as being rather nascent, but promising at this point. And so the basic theme of our book, which I think should be very familiar to this audience, is that we need to embed social values in algorithms. And one of the things that's very challenging and important about this agenda is if we're going to embed social values in algorithms, if we're literally going to, in our code, enforce constraints regarding things like fairness or privacy or interpretability or explainability, it means that we need definitions. We need to be precise and have good definitions, and we need to then develop and study their consequences. And, I don't think I need to tell this audience that computer scientists are far from the first community of people or scholars that have thought deeply about things like privacy or fairness. But what's special about the agenda that we're talking about here is that, if you look at the work by, moral philosophers or legal scholars on fairness, those communities did not have the burden of being so precise by what they meant by fairness that it could literally be, expressed in Python code. And it turns out that one of the interesting things about being that precise is that you often discover flaws in your intuitions about these concepts that you really weren't going to discover any other way. And so I'm going to give a couple of examples of that in the course of this talk. So our book is, in general, arranged as kind of chapters around what we might think of as different broad social norms. So there's an early chapter about privacy, there's a chapter about fairness, we discuss accountability, interpretability, and morality. And if you're wondering if what the shading is indicating here, the shading is our subjective opinion about the relative maturity of these different areas. So in our view, the study of algorithmic privacy, and specifically differential privacy, is perhaps the most mature of the different disciplines we consider in the book. Algorithmic fairness is off to a good start, but maybe a decade behind where privacy research is. And in our view, accountability, interpretability, and fuzzier things like morality, or even worse, the singularity, which is invisibly written at the bottom of this list, are all interesting topics, but we feel are very fledgling in the sense that there aren't even plausible, satisfying definitions yet. And I'll maybe say a little bit more about that towards the end if there's time. And so what I want to do today is spend most of my time just doing two little case studies or vignettes, one around privacy, which I've again kind of modified and added a little bit of maybe slightly more advanced material, because I know this audience knows quite a bit about privacy in general and differential privacy specifically. I sat in on some nice talks on these topics in this conference yesterday. And then I'll talk about something that perhaps people here have thought less about, which is algorithmic fairness. And then I'll spend a little bit of time towards the end talking about a bit of a left turn that the book takes midway through. But it's an important and I think thought-provoking left turn that might be interesting to this particular audience. And so that's the rough game plan. And so I'm just going to roll forward. So let me talk a little bit about privacy, which, I've worked a fair amount in differential privacy, but I would not consider myself a lifelong privacy researcher the way many people in this community would, or that my co-author Aaron Roth would. But probably many people in this audience are familiar with Cynthia Dork's famous quote, "Anonymized data isn't," which kind of has kind of two interpretations to it. One is that, either anonymization doesn't work in the sense that you can re-identify people from anonymized data, or you've done so much redaction and coarsening of your data that it really isn't useful data anymore. And so normally I would spend a fair amount of time on this slide, but I think I can save some time here for other topics a bit later by just saying that, one of the things we try to do in the book is emphasize the importance of good definitions. And we also emphasize the fact that it's possible to have precise definitions that are just bad definitions. And we argue in the book that, in our view, definitions around anonymization or removal of PII and the like are kind of fundamentally conceptually broken beyond repair, in the sense that they're brittle and kind of misleading. And so, again, just to save a little bit of time here, what I'm showing here is like a toy example where you have two different medical databases, and in each one of them, for kind of privacy concerns, you've decided to redact certain columns altogether, like name. You've coarsened other columns like age and grouped people into decades rather than providing precise ages. You've done a bit of redaction on zip code, and these databases meet the formal definition of k-anonymity. So the top database is 2 anonymous with respect to age, gender, and zip code, and the bottom database is 3 anonymous with respect to those same attributes. And there's kind of two big problems that we talk about with k-anonymity, and just quickly to remind people, k-anonymity means, or k-anonymity with respect to some subset of the columns means that if I look at any set of values in the database projected onto those columns, there are at least k copies of those exact values elsewhere in the database. So if I look at the top database and I select on age being 50 to 60, female, and a 191 zip code, there are 2 records that match that description, and for any other values I chose for those attributes, there would again be at least 2 matches. And so the vague heuristic idea here is that somehow if I have a k-anonymous database, even if I know something, I have a neighbor, Rebecca, and she's 57 years old, and I happen to know that she's visited these 2 hospitals, I have some confusion about what her actual diagnosis is, for example. And of course, one problem with this is that my neighbor, Rebecca, like in the top database, I would know that she either is HIV or has colitis. Of course, she might already consider that to be a privacy violation. And one might try to counter argue, well, in a real database with tens of thousands of medical records, if it was 100 anonymous rather than 2 anonymous, I really wouldn't get much useful information at all. The real problem with anonymity definitions, of course, is that they do not degrade gracefully. And more specifically, the real conceptual problem is that definitions of this kind pretend like the data set in front of you is the only data set that's ever going to exist now or in perpetuity. And if there was ever such a time, it is certainly not the modern era. And so the real problem is that I can have multiple databases, each of which in isolation meets some definition of anonymity. But when I take the join of those databases, like the top and the bottom ones here, then I'm able to essentially do triangulation and back out or re-identify specific people. So in this case, I would know from the join of the red columns in the top and the ones in the bottom that my neighbor Rebecca was HIV. Okay, so one of the points we make in the book is that to the extent that we have laws and regulations in this country or elsewhere that bother, or corporate policies for that matter, that bother to be precise about what's meant by privacy, they unfortunately almost uniformly rely on definitions like the ones that we're discussing here, removal of PII and the like. And so It is possible to be precise and give, clear definitions and then to have regulations around them, and yet to have gotten it all wrong, which is essentially what we're arguing is happening in the case of anonymity-based definitions. And so the next thing we kind of take the reader through is like, well, okay, so that's a bad definition of privacy because it's too weak. It's not really providing any meaningful privacy guarantees. And so then we go in the opposite direction and say, like, well, what would be like a strong definition of privacy? And again, I'm sure that many of you have kind of thought through these topics before and know the history. And so, another type of privacy definition, which I'll just state informally, of course, as many of you know, it can be made and has been made precise before. I could kind of give definitions of privacy that I would call the no harm whatsoever definition. And so what do I mean by no harm whatsoever? So you have your medical record. I'm asking you to contribute it to some study or analysis or computation that I'm going to do. You're deciding whether you're comfortable with that or not. And I tell you, well, look, suppose I could promise you that nothing, whatever it is you're worried about, whatever harm you feel might come to you as a result of the analysis or study I'm going to do, suppose I could somehow promise you that no harm whatsoever would come to you as the result of the study that I'm about to do that would include your medical record. So that sounds like a great definition of privacy if we could meet it. It's certainly a strong definition. And of course, the problem with this definition is it's too strong in that it would essentially prevent us from, many valuable uses of data. So here I'm showing you the cover page from a famous article, from a series of articles by Dahl and Hill in the 1950s. They were the British doctors who first established the strong connection between smoking and lung cancer. And they basically did this by asking every doctor in the UK at that time whether they would contribute their medical record to their study, and 2/3 of the doctors opted in. And the result, of course, was the overwhelming evidence of a link between smoking and lung cancer. So suppose you were a doctor in 1950 in England and you were a smoker, and probably you were because everybody smoked back then. There was no social or medical stigma associated with it. And so you wouldn't have hidden the fact that you were a smoker either. Everybody would have known it. Everybody who knew you would know it. And we could say that as a result of this study that included your medical record, real harm came to you, right? Because in kind of Bayesian terms, after this study is released, everybody's posterior belief that you might have lung cancer will increase, okay? So the study was done, your medical record was included in it, and now some real harm has come to you. In fact, in the United States at least, your insurance company, knowing that you were a smoker, might, as a result of this study, decide to increase your premiums. And so we could say that quantifiable economic harm has come to you. And so if we adopt this no harm whatsoever definition of privacy, we wouldn't be able to make valuable, practical, and societal uses of data like the Dahl and Hill study. And so, one way of thinking about differential privacy is that it starts with this no harm whatsoever definition and slightly modifies it to make it still have sort of the strongest practical privacy guarantees that allow us to do things with data. And so if you think about the no harm whatsoever definition, really I was asking you to compare two alternative worlds, right? One is in which I do the Dahl and Hill study with your medical record included. And B is the case where I just don't do the study at all, okay? And the no harm whatsoever definition asks that the harm that comes to you doing the study with your data included should, not be greater than the harm that would have come to you if we didn't do the study at all, period, okay? And the key observation, kind of conceptual observation behind the definition of differential privacy is that, it's not like in the Dahl and Hill study, your medical record was the key piece of evidence that allowed them to discover the connection between smoking and lung cancer, right? Rather, any sufficiently large database of medical records would have been enough sufficient to establish that connection, because the connection between smoking and lung cancer is not a fact about you. It is a fact about the world that can be discovered with any sufficiently large data set. And this leads us to the definition of differential privacy, which I generally don't give in this talk because I'm speaking to non-technical audiences, and here I won't do it for a different reason, which is I'm imagining that pretty much everybody is familiar with it at some level. But at a high level, you know, what it's doing is taking this no harm whatsoever definition and sort of changing counterfactual B. So rather than comparing doing the study with your data to not doing the study at all, we compare doing the study with your data included and doing the study with everybody else's data except yours included. So we compare the output of a computation or analysis given n medical records as input as case A, and n-1 as case B, where the -1 is the removal of your medical record or any other individual's medical record. And what we ask is that the output of the algorithm in these two situations be controllably close or negligibly different. And so in particular, as people probably know, the definition of differential privacy demands, at least in non-trivial cases, that algorithms be randomized, right? You essentially achieve differential privacy by adding noise to your computation or to your analysis. And you ask that the distribution over outputs induced by that randomization on any pair of neighboring databases be controllably close. And one of the very important things about the definition of differential privacy, which again, I realize people here are quite familiar with, but I'm going to use this as an analogy when we talk about fairness, is that it provides a knob, right? And this knob is kind of the privacy parameter, which basically says, well, how close do I demand that these two distributions be, right? So if I ask for 0 differential privacy, that means that these two distributions, the one including your data and the one not including your data, have to be identical. And as we allow larger and larger values of the privacy parameter, we're allowing those two distributions to be further and further apart. And this in general leads to a trade-off, right? It leads to a trade-off between the strength of the privacy promise made to individuals whose data is being used in the computation and the utility of that computation. Again, people are probably familiar with this, but one curiosity about differential privacy is that the first instance, to my knowledge, of a differentially private algorithm predates the definition of differential privacy by 40 years. And this is the randomized response protocol from kind of the social sciences. So in randomized response, the goal is to survey people in a way that elicits truthful responses, the answer to some question that might have an embarrassing or stigmatizing answer. So suppose I want to survey, you know, citizens in Philadelphia as to whether they have violated social distancing guidelines, and maybe people will be reluctant to admit that they have. So there's some stigma associated with the yes answer. And so in randomized response, what I ask everyone to do is in the privacy of their own home to, let's say, flip a coin, right? And if the coin comes up heads, which is this top branch here, you answer truthfully whether you've violated social distancing or not. On the other hand, if the answer comes up tails on this bottom branch, then you're asked to flip the coin again and just use the outcome of the coin to answer yes or no, regardless of what your true answer is, okay? And so the great thing about this example is that it's immediately clear that this protocol provides everybody strong, plausible deniability without even giving a formal definition of privacy, right? Because in this protocol, if you confront me and say, hey, you know, I learned that you answered yes to the question of have you violated social distancing guidelines in the protocol I gave you, I can say, you know, that's right. I did answer yes because I followed the protocol you gave me, and my first coin came up tails, so I went down here, and my second coin came up here, and so I answered yes. And so I can say, no, I haven't. Everybody can simultaneously claim that they haven't violated social distancing, even if their answer was yes. So everybody has strong, plausible deniability, and they also have differential privacy. And more generally, if I parameterize this first step, and I have you go answer truthfully with probability p and answer randomly with probability 1 minus p, you will satisfy, you know, log 1 plus p over 1 minus p differential privacy. But the other thing that's kind of immediately obvious with just a little bit of arithmetic is that if everybody follows this, you know, plausible deniability / differentially private protocol faithfully, then we can also back out extremely accurate answers to the question about what fraction of the population has violated social distancing guidelines. So even though I essentially get very little information about the true answer of any particular individual, if everybody follows this protocol, you can just work out some simple arithmetic and see that if everybody follows this protocol, and I have n people answering this protocol, then I can get an approximation to the true fraction of violators of social distancing that's accurate to within plus or minus 1 over square root of n, and of course an expression that will also involve p as well. And so this is like the typical form of a differentially private, theorem statement. You have two parts to it. You have the privacy part and you have the utility part. You basically say if everybody follows this protocol, everybody will enjoy a certain amount of differential privacy. And then you can also say the second part of the theorem is a utility statement that says, and the surveyor can back out answers to the aggregate question that they were interested in that have a certain accuracy to them. Okay, and there will be a trade-off between the amount of privacy and the accuracy, or more generally the utility of the computation. Okay, so differential privacy was introduced in about 2005, and now 15 years in, there's a very, very extensive, rich body of literature establishing, both what we can do with differential privacy and what some of the limitations are. But I would basically say that the news is extremely good. I mean, as a relative newcomer to this topic, I maybe started working in this area 5 or 6 years ago. When I first saw the definition of differential privacy, I looked at it and I said, like, well, that is a very good definition of privacy, in the sense that if you can, provide that guarantee, it's a strong promise to individuals about the privacy that they enjoy. And my main worry when I looked at it was like, well, maybe it's too strong, kind of like the no harm whatsoever definition. Maybe you won't be able to do useful computations with it. And good news is that that's turned out to not be the case. And so one example is that I say with very little exaggeration that every single technique we are used to and use widely in statistics and machine learning can be made differentially private. And what I mean by that is, it is not the case that the original algorithms are themselves differentially private, but they all have differentially private variants. So, back propagation for neural networks in its original form is not differentially private, but there are modifications of it that are differentially private. Sometimes you actually get lucky. So in particular, stochastic gradient descent, which is now one of the most popular methods for training deep neural networks. As the name suggests, stochastic gradient descent already is using noise as part of the learning process. And it turns out that, if you use stochastic gradient descent with the right amount of noise, you will also for free get differential privacy. But more generally, whatever your favorite method is, boosting support vector machines, decision trees, neural networks, etc., all of that can be done in a differentially private way. And so in the past 5 years, differential privacy has kind of been getting out of the lab, or maybe more accurately off the whiteboard, and kind of into practice. So a couple of the large technology companies, including Google and Apple, were early adopters and used differential privacy to essentially gather behavioral statistics. So, Chrome for a number of years has been using differential privacy to gather information for things like autocomplete in a differentially private fashion. And Apple has been for a number of years in iOS using differential privacy to gather aggregate statistics about app usage in a differentially private fashion. But now we're starting to see some more large-scale, serious use cases. So here I'm showing you a screenshot from a site at Google, who for a number of months now has been releasing kind of what they call community mobility reports for COVID-19. And so the high-level idea here is, maybe they're gathering, of course, geolocation data from people's devices, and they're using that to kind of create heat maps of different geographical areas. So you can go look up your city or location and perhaps see a heat map that basically shows you here are the areas which, according to the geolocation data that Google has collected, where are the areas in your city where people seem to be gathering in uncomfortably large numbers for uncomfortably long periods of time in uncomfortably close proximity, and maybe you would want to use that information to avoid those areas if you're worried about COVID. And of course, they're quite aware that there might be privacy concerns in using geolocation, this data this way. And so they're releasing it in a differentially private way. And at a high level, what that means is rather than releasing the, numerically precise heat map statistics, instead of telling me, hey, Michael, here's exactly how many people were gathered in close proximity at the Whole Foods 3 blocks from here over the last week, they're essentially going to add noise to those statistics that provides differential privacy. And so this is like a nice use case of differential privacy, and a rather straightforward one, because these are just simple counts that you're trying to release. And so you can just, add noise independently to each one of those counts and get differential privacy. There's been, some of you are probably quite aware that in these days there's been discussion about kind of more granular use cases of differential privacy in the battle against COVID. And in particular, there's been some discussion about whether differential privacy might play some role in contact tracing. And curiously, Aaron and I and colleagues Stephen Wu and Grigory Yaroslavtsis thought about this problem, way back in 2015, not in the context of COVID, but again, kind of in the context of contact tracing. And our primary motivation then was the huge controversy over the NSA's use of telephone metadata in the United States for kind of contact chaining for counterterrorism. But when we wrote this paper, it was also at the same time as the Ebola outbreak, and there's quite a bit, at a high level, quite a bit of similarity in, of course, contact tracing or link chaining or contact chaining for counterterrorism using telephone metadata, and things like contact tracing for an infectious disease. And in its vanilla form, differential privacy is not a good match to these use cases, because differential privacy, by definition, provides everybody differential privacy. Every single individual who's involved in some computation is simultaneously provided a privacy guarantee by the standard differential privacy definition. And in things like contact tracing, by definition, that's not what you want, right? So you need to acknowledge in contact tracing that people that have been identified as infected, may have lesser privacy guarantees than people who are not positive. And the whole point is to use the people's data who are positive to trace other people who should be tested or quarantined, perhaps. And so we thought about this in this earlier paper. There is a solution you can give. And in particular, to say at a high level, what we do in this paper is we basically first modify the definition of differential privacy to divide, the population into two rough categories: people whose privacy should still be protected under the guarantees of differential privacy, and the targeted or infected individuals whose privacy does not enjoy that same promise. And you could imagine there being more than two levels of this, but we just considered the kind of the binary case. And then what we do is we say, like, well, let's look at a broad class of algorithms that for things like contact tracing, where at a high level, what you might do is you start with some seed set of individuals that are infected. And what you're going to do is use some kind of local search algorithm in a graph to try to identify other people who should be tested and possibly quarantined. And we're pretty general about what type of search algorithm you can use. At a high level, we identify a class of search algorithms that are essentially identified by some statistic of proximity. So like a typical statistic of proximity would say the closeness of two individuals, X and Y, in a social network would depend on the number of their shared contacts. So that's, or shared neighbors, common neighbors. So that's a statistic of proximity. And kind of the main result of the paper was a modification of that class of algorithms that adds noise in a particular way that promises differential privacy to the uninfected individuals in the social network, while still trying to effectively find the infected individuals in the network. And this is just kind of an image showing a particular algorithm in this local search category operating on the left in the non-private setting and in the right on the private setting. And the blue individuals are sort of people that have been kind of identified or touched by the algorithm, and the red are the infected individuals. And at a high level, what you do is the normal and differentially private thing. You add noise to your process. So, in this case, the noise actually helps the private algorithm discover like a new connected component of infected individuals. But in general, you would expect some degradation of performance, and what these plots are showing is like in some large scale simulations on kind of publicly available social network data, showing essentially the utility of a non-private algorithm in blue. So higher is better here. This is the number of infected individuals found as a function of the number of steps of the algorithm on the x-axis. And so blue is sort of showing you the non-private algorithm. The red traces are showing you individual runs, and each run, of course, is different because of the randomization and differential privacy. And in general, in the aggregate, the average performance of the private algorithm, which is this kind of red envelope here, is worse than the non-private algorithm, but not by much. And so, this is kind of, I think, a very crude proof of concept that you could adapt the methods of differential privacy to do things like contact tracing. What I haven't done, and what I'm honestly skeptical of, is whether the specific methods we propose in the paper would really work at scale for the type of contact tracing that would need to be done with COVID. I'm kind of concerned just the amount of, you would either, the amount of noise you would need to add to give meaningful privacy guarantees to individuals in such a large scale case would kind of obviate the usefulness of the method. But the idea is out there, and maybe somebody will take it further than we have. And finally, and I want to get to fairness in a minute. Probably many people in this audience are aware that the real moonshot test case for differential privacy is coming in the US 2020 census, where they have made the decision and promised that every report and statistic released from the raw underlying census data will be done under the constraint of differential privacy. And so this is a great ambitious test case for differential privacy. It's not without, it's not without detractors. And so in particular, here's a recent New York Times op-ed piece that basically points out that, the noise of differential privacy, when added to the census counts of small communities, might entirely disappear some small communities, and that there could be real consequences to this in the form of the fact that, lots of federal allocation decisions are made based on those counts. And that, that's true. It is not the case that differential privacy does not come without costs to utility, accuracy, or other things. I should point out that, right, one of the interesting tensions about the census use case is that there's a non-trivial community of academics who've essentially carved out a career making interesting use of the way that the census previously released their reports. And at least one of those people is an author on this op-ed piece. So not only might the noise of differential privacy make some small communities kind of quote unquote disappear, it might disappear the research agenda of these individuals as well. Okay, let me talk about algorithmic fairness now, which I think is probably something people are less familiar with. So first of all, if we kind of compare the success story that I think differential privacy is to the work that's going on in algorithmic fairness, fairness is definitely in a much more nascent state. It's much more of a work in progress. And in particular, while we argue in the book that differential privacy is kind of the right definition of privacy, we already know that the study of algorithmic fairness will necessarily be messier than that, in that there won't be a single definition. So in particular, in the past few years, there have been a couple of papers that, very nice papers, that take the following form, right? You read the paper and the authors say, well, look, why do we have all these different definitions of fairness in the literature right now? Why can't we sort of consolidate these into the one correct definition? And then they sort of propose an axiomatic approach. They say, like, well, here are 3 properties that any good definition of algorithmic privacy should meet, right? And you, the reader, you look at these 3 properties and you say, yes, 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 of course, these are extremely weak properties. I would definitely want all 3 of these properties to hold, and I'd probably want even additional stronger properties as well. And of course, the punchline of the paper is, well, here's a theorem showing that it is mathematically impossible to simultaneously achieve these 3 properties, except in kind of trivial, unrealistic cases. So in the same way that in differential privacy, there's a trade-off between the amount of privacy promised to individuals and the utility or accuracy of computations, that same trade-off between fairness and accuracy will exist. But it's even worse than that. There will even be trade-offs between different notions of fairness. And to make this a little less abstract, it literally might be the case that you have a data set in which, by demanding more fairness, let's say by race, you necessarily get less fairness by gender. So there really might be stark trade-offs between the amount of fairness you can provide to different demographic groups, okay? And we're only just beginning to understand what those trade-offs look like. But I'm getting a little bit ahead of myself because I know that people in this audience may not be that familiar with algorithmic fairness or machine learning more generally. So again, what I want to do is kind of give a little toy example, kind of as I did with the medical databases, just describing why it is that machine learning can result in unfair models, and also just say, give one precise example of what we might even mean by unfair, okay? And, oftentimes, when we go around discussing these topics with diverse audiences, machine learning is mysterious to a lot of people, right? The whole process is this opaque black box. And, sometimes it gets suggested that, oh, well, maybe the way we get to unfair discriminatory models is by sloppy engineering, or scientists misapplying the principles of machine learning, or, even worse, that there are evil, immoral, programmers, kind of putting statements into code that say something like, well, if somebody's race is this, then do this, otherwise do that. And the truth is actually worse than all of the above. The truth is that the real problem is with the underlying principles of machine learning in the first place. And this example will kind of, I think, illustrate one reason why that's true. So suppose Aaron and I were asked by the Penn Admissions Office to help them, use machine learning to develop a predictive model for admissions decisions to the University of Pennsylvania. And so in this toy example, we have a cloud of data points here, and each one of these data points represents not just somebody who applied to Penn, but somebody who applied and was admitted and actually came to Penn. So we have historical data, if you like. We have historical data on students who were admitted and came to Penn, and the pluses and minuses in this cloud of point indicate whether that particular student succeeded at Penn or didn't. Okay, and for the definition of success, pick any quantifiable, objectively measurable outcome. Like, one example would be graduating within 5 years of matriculating with at least a 3.0 GPA. Okay, and so the pluses in this cloud indicate past students at Penn who met that criterion of success, and the minuses indicate ones that didn't meet that, okay? And these points are plotted according to the high school GPA of the applicant and the SAT score of the applicant, okay? And so you can sort of see in this cartoon, in general, the successful students were the ones that had higher high school GPAs and SAT scores. And the students that didn't succeed were the ones with lower scores. And without knowing anything about machine learning, if I asked you to use this data to build a predictive model, you very might well eyeball it and say like, well, if I use this simple linear threshold classifier, if I basically predict that everybody above this blue line is going to succeed, anybody below it is going to fail, I'll do a pretty good job. It's not perfect, right? There are some false positives here. These are students that I would have admitted who actually ended up failing. And there's some false rejections here. These are students who I would have rejected that in fact did succeed. Okay, but it looks like it does a pretty good job. So suppose I told you that this wasn't the entire historical data set, but rather there was a separate group or demographic. So these are the green subgroup of the overall population. Suppose I told you there was also an orange population that looked like this, okay? And there's a few things I want to point out about the orange population. One is that the orange population is a minority in the literal sense that there are many, many fewer orange points in this data set than there were green points, okay? Observation number 2 is that there seems to be something systematically different about the orange group. In particular, it seems like the entire cloud of orange points is kind of shifted downwards on the y-axis, i.e. the SAT scores seem to be systematically lower in the orange population than the green population. And if you asked me to motivate this story, I might suggest like, well, maybe the green population is a wealthy demographic. And so they can afford financially and in terms of time to pay for SAT preparation courses and to take multiple retakes of the exam and take the max of their scores, all of which takes time and money. And the orange population kind of can't afford any of that. So they do a little bit of self-study, they take the exam once and they take the score they get, okay? But notice that the orange population is not less well qualified than the green population. So if you looked at the green population and counted carefully, you would have discovered that slightly less than half of the green population succeeded. And here it's exactly 50-50. There's an equal number of orange pluses and orange minuses. And if you ask me to build a classifier for just the orange cloud, you know, there's a perfect classifier, at least on the historical data, which is this purple threshold classifier that doesn't make any mistakes, okay? So now, if I take the combined population, and I now again ask you to find the classifier that maximizes the overall predictive accuracy of your model, you will unfortunately find yourself picking the exact same model that you did on the green population alone. Because the problem is if I try to move this classifier down enough to admit these 5 successful orange students, I will pick up so many green minuses along the way that my overall error will actually increase, okay? So the problem here is a simple one. If I just use the standard principles of machine learning, which in general say like, well, on your historical data, maximize the predictive or historical accuracy, like, you know, maximize your training accuracy or minimize your training error, which is basically, you know, in a nutshell, the overriding principle of pretty much all of modern machine learning, you know, except with maybe some complexity regularization, right? I don't want to build an overly complex model. But here I'm just taking lines, so that's not really a concern. So the problem is that the very principle that asks me to maximize my predictive accuracy on the overall population results in measurable unfairness. And now we can basically identify a particular definition of unfairness. So the thing that's unfair about this blue classifier is that the false rejection rate, i.e., people that would have been successful that are rejected, the false rejection rate on the green population is close to 0%, and it is 100% on the orange population. So I could basically introduce a numerical definition of unfairness, which is what is the disparity between the false rejection rates on these 2 subpopulations. And this blue model basically is as unfair as possible. So by maximizing the overall accuracy, I have landed on the model that is the most unfair to the orange population. Okay, now there's an easy, obvious fix to this that you might have already seen some time ago, which is like, well, why don't I have a 2-part model? Why don't I say like, well, if you're from the green population, I'm going to apply this blue classifier here. And if you're from the orange population, I'm going to apply this purple classifier here. And it's not hard to see that if I have that 2-part classifier, not only do I eradicate the disparity in false rejection rates, they're now both close to 0, I will also improve my overall accuracy on the population at large, okay? So the problem with this is that, unfortunately, once again, like definitions of anonymity for privacy, to the extent that we have laws and regulations that basically commit to what fairness means, they explicitly forbid this kind of model. In the case, as I've kind of tried to plant in your head, in the case, for instance, in which green and orange here represent racial groups. So in consumer lending applications in the United States, it is against the law to use race as an input in any model or algorithm or any process for making lending decisions, okay? And I'm sure that this was a well-intentioned law back at the time it was developed. It again is this kind of magical, it's like K-anonymity, it's like magical thinking. It's like somehow by forbidding the use of race in the process, I'm providing some notion of fairness by race, okay? So this example is showing you how badly that can go wrong. It's not just that this definition is kind of weak, it's having the exact opposite effect, right? It is having the effect that, you know, if I care about overall accuracy and you also forbid me from using race as an input, you guarantee harming the very group that you were trying to protect with that definition, okay? So like notions of anonymity for privacy, we argue in the book that definitions of fairness that act by forbidding what kinds of inputs a model and algorithm can use are fundamentally broken. And a far better type of definition is to let algorithms use any inputs that they want, but to explicitly constrain the output behavior of the model that you find. So in particular, in an example like this, we would basically say, find the model that maximizes the overall predictive error, but subject to the constraint that the false rejection rates between the two populations can't be greater than some specified amount. And what is this specified amount? Well, that's a parameter, right? In the same way that epsilon, the privacy parameter, is a parameter of the definition of differential privacy, we now have a definition of unfairness, which is the disparity in false rejection rates. And we could basically say, well, look, I want that disparity to be 0%. There can be absolutely no difference in the false rejection rates between these two groups. Or I could relax that and say, well, okay, you can have 1% disparity, 5% disparity, et cetera. And if I let that be 100% disparity, then it's like I'm ignoring fairness entirely, right? And just going for overall accuracy. And so as I relax the constraint, the fairness constraint, I'm going to get my better and better predictive accuracy. And you can literally, on real data sets, trace out what the Pareto or efficient frontier looks like in this trade-off between these two quantities, right? So, for example, on the left here, this is from a real data set in which there are fairness concerns for some demographic subgroups. And what I'm showing you here on the x-axis is the predictive error. And on the y-axis, I know it's hard to read the legend, but on the y-axis is some quantitative definition of unfairness, like the disparity in false rejection rates. And of course, what we wish we were at the origin. We wish we could have perfect predictive accuracy and zero unfairness. Of course, we're not going to get to the origin even without a fairness constraint, because in real machine learning problems, you rarely get to zero predictive accuracy out of sample, at least, because, you know, real machine learning problems are hard. But now you can see that there's a distinct trade-off here, right? So each one of these red dots is a different model. If you like, it's a different linear classifier, it's a different neural network, it's a different decision tree. And one choice I have is this choice up here in the upper left, where I'm ignoring the fairness constraint entirely. So I have the highest unfairness value, but I get the lowest error. At the other extreme, there's this model over here, which has the highest error, but zero unfairness. And in between, I can get things in between, right? And, you know, the shape of these curves matters, as do the actual values on the axes here, which I know you can't read, as do like what's at stake, right? So we might very well make very different choices on what an acceptable trade-off is between fairness and accuracy, depending on whether what's at stake is whether I show you an irrelevant ad, you know, in your Google search results, versus whether I give you parole or not in a criminal sentencing application, or what kind of medical care I give you. right? And in some sense, like these pictures are as far as the science can take us, right? It shouldn't be me, the computer scientist or machine learning researcher, who tells, whoever gave us this data set, like, okay, here are the different choices you can make trading off accuracy for fairness, and here's the model you should choose, right? The stakeholders should make those decisions. And we argue in the book that pictures like this are a good interface between people like us, scientific researchers, and people like policymakers, regulators, legal scholars, and the like. And we're not there yet. We're not yet at the point where the machine learning community has become adept at generating these curves and explaining them to people with less technical background. We've not gotten yet to the point where people with less technical background can kind of intelligently look at these plots and make decisions about them. But I think that era is coming, and we need to get there soon. Okay, so let me just spend a few more minutes describing really what we talk about in the second half of the book. And in the second half of the book, we kind of take what I describe as kind of a wide, long left turn, but I think it's an interesting and important one. So if you think about what I've said so far about privacy and fairness, and step back from it a little bit, in those settings, it really was fair to think about algorithms, algorithms and algorithmic decision making as being the perpetrators and ordinary systems being the victims, right? So in a lending or college admissions decision, there's some statistically trained model that's making accept or reject decisions. And it could be that you or your kid gets rejected from the school of their choice by an algorithm, and it's an unfair decision in the technical sense that I described. It's a false rejection, and so it's really the algorithm kind of perpetrated this harm on an individual, and even worse, the individual may not even know that it was an algorithm that perpetuated that harm. Okay, in the second half of the book, we consider settings in which algorithms, again, are playing a central role, but it's not quite so easy to exclusively blame the algorithm for the kind of societal misbehavior that occurs, right? And this often is the case in situations in which there is an app, if you like, and what that app is trying to do is mediate the competing preferences of a large population. So perhaps the cleanest example of this are navigation apps like Waze and Google Maps. And so, at some level, what could be better than these apps, right? Especially compared to an earlier era where you would have like fold out maps in the glove compartment, and the only real-time traffic information you had came in hourly or half-hourly radio reports that only covered the major roadways. So now what could be better? I just like plug into Google Maps my starting point and my destination, and in response to the real-time geolocation data of tens of thousands of other drivers in the Philadelphia area, it actually computes what is my shortest driving time path, and even suggests some alternatives in case I care about those alternatives. And as you probably all know, these days, these apps will also tell you, in progress, if there's a better or faster way for you to go, okay? So like what could possibly be the downside here, right? You've got this app that is kind of taking everybody's geolocation data in, and then on each of our behalves, kind of computing the shortest driving time for us, right? Well, if you think about this, this is a game, right? It is literally, technically a game in the game theoretic sense of that term, right? It's an incredibly complicated, large scale game with tens of thousands of players, right? But it is a game, right? Each one of us has a utility function, right? I have a origin, I have a destination, and my utility function is spend the minimum amount of time driving possible, okay? And you all have similar utility functions. And what these apps are doing is taking all of those, those preferences in and using the real-time traffic data. And they're essentially, in game theoretic terms, computing all of our best responses simultaneously. And and so what these apps are doing is nudging us towards a competitive equilibrium. Literally, in this case, it is nudging us all towards the Nash equilibrium of this game. And if you know any game theory, you will know that just because something is in equilibrium doesn't mean it's a good outcome, and it doesn't mean it's a good outcome for anyone, right? And prisoner's dilemma, of course, is the classic example of that. And so, here it is the case that there is an algorithm involved, and that there might be kind of antisocial behavior that results in the use of that algorithm. And in particular, it's been well known in the transportation theory literature for many decades that the amount that we're collectively driving in the aggregate at the Nash equilibrium of a game like this might be considerably more than some alternative solution that was not a competitive equilibrium. And so in particular, it could be, for instance, in real settings, in real cities, that we're all collectively, by using these apps, driving up to 33% more on average than we could under some other centralized solution that's not a competitive equilibrium. And so in the second half of the book, we kind of discuss these types of scenarios where you can't just sort of fix the app or the algorithm the way you can for differential privacy or fairness. You have to take into account the preferences and behavior of the users of the algorithm as well. And there's still things that you can do, but from a technical standpoint, the tools of game theory become very important. And even not just as kind of as a descriptive way of thinking about these problems, but as a prescriptive way. And in particular, one of the things that I think that's quite interesting that's going on these days in the machine learning community that also has applications to fairness and differential privacy is the use of game theory as an algorithm design principle, where you literally set up as an artifact of your algorithm a game between two players, and use the interactions between those two players to find a solution. And so in particular, those of you that are familiar with the literature on generative adversarial networks and machine learning, those algorithms very much have this flavor. You set up a game between two players, and in the case of differential privacy, for instance, you might set up a game between two players, one of which you might think of as a discriminator, and the other one is you think of as a generator in service of generating a synthetic differentially private data set. And so this is a very active area of current research in machine learning, in algorithmic fairness, and in privacy as well. And so in the second half of the book, we kind of consider these types of situations. I'm going to skip that slide. And then we have kind of a final catch-all chapter about some, other kind of social norms that are receiving a great deal of attention these days, especially things like interpretability or explainability of models. And, you can go read what we've written about those topics, but the reason we kind of put them into a catch-all chapter at the end is because in our view, despite how important these topics are and how natural it is that regulators and ordinary people would want explanations for algorithmic decision-making, we just don't think the right definitions are there yet, for a variety of reasons. One is that when you say you want an explanation of something, you could want an explanation of many, many different things in the machine learning pipeline. You might want an explanation of the data itself. You might want an explanation of the training algorithm, like backpropagation. You might want an explanation of the model output by backpropagation, the actual neural network found, or you just might want an explanation of individual decisions, like why was I rejected for this loan? And what explainability should mean from a technical standpoint is very, very different depending on which of those components of the machine learning pipeline you're trying to provide an explanation of. And then I think the other real kind of missing research in this area is really kind of a behavioral one, which is once you start talking about things like explainability or interpretability, the audience matters greatly. And in particular, the level of numeracy of that audience matters greatly. So if I'm trying to explain deep learning to somebody that comes from a statistics background and already understands what logistic regression is, for instance, I can have a very, very different conversation about explaining how deep learning works than I could with somebody who never took high school mathematics. And so I think there also needs to be human subject work that actually explores what different audiences can understand and what constitutes a satisfying explanation to those different audiences. And there's a very small amount of work that's going on in this area in the past couple of years, including some very nice stuff coming out of Microsoft research. But I think this is entirely wide open and also necessary for making progress in those types of social norms. And so with that, let me stop and take any questions. Thanks for listening.